In this video, we're going to continue our test review on trig equations and identities, starting here at number 11. And number 11 and 12, here we're asked to verify these identities. Now remember, with identities, we've got a statement that says two different expressions are equal to each other, and we're trying to prove that it's equal. So we can't be moving things back and forth on either side. You can only do that when you have an equation, when you know things are equal. And so first thing I'm going to do is put a wall here between my two sides. And remember, you can work on either side, and you want to keep working until both sides look the same. I'm going to start over here on the left. I have cotangent x plus tangent x. And so I'm going to change those to sine and cosine. Cotangent x I can change to cosine x over sine x, and tangent x would be sine x over cosine x. Now I've got two fractions here that are being added together, and so I'm going to get a common denominator and go ahead and combine the fractions together. Anytime you've got two fractions being added or subtracted, a good strategy is to get a common denominator and go ahead and add or subtract them. So my common denominator is going to be sine x times cosine x. And on my first fraction, if I change the denominator to sine times cosine, I need to multiply my numerator times cosine also. And so I would end up with cosine squared x. Plus, in my second fraction, if I change the denominator to sine times cosine, I need to multiply the numerator times sine also. And I get sine squared x. So now I have cosine squared plus sine squared over sine times cosine. Well, hopefully you recognize cosine squared plus sine squared, it's equal to 1 over sine x times cosine x. Okay, now at this point, I think I'm going to go to the other side, see what we can do over here. I can change cosecant to 1 over sine x, and I can change secant to 1 over cosine x. And if I multiply those two things together into one fraction, I get 1 over sine x times cosine x. And now both sides are the same, and so I have verified that the identity is true. Let's look at number 12. Same thing again. I'm going to start by putting up that wall. And on this problem, we're going to use a pretty special strategy, and I have to admit I'm not sure that we did one like this in class. So let me explain this strategy. If I look at what I'm starting with here, 1 minus cosine over sine is equal to sine over 1 plus cosine. There's really no identities that I can use to replace anything. It would be nice if I had 1 minus cosine squared, because then I could use one of the Pythagorean identities, and that might help me get somewhere. But in this case where you don't have any identities that you can substitute, one thing you can always do is multiply by 1. If I multiply by 1, I'm not changing the value of anything. I'm just going to change the way it looks. So I'm going to choose a really special one to multiply. And in this case, what I'm going to choose is 1 plus cosine theta over 1 plus cosine theta. And I'm just doing this on the left side for now. The reason that I chose that is because I have 1 minus cosine theta, and if I multiply that times 1 plus cosine theta, notice it's the same terms, but one's minus and one is plus. So when I multiply that out, it's just going to be a difference of squares, 1 minus cosine squared theta. And in the denominator, I'm just going to leave that as sine theta times 1 plus cosine theta. So I've carefully chosen my 1. This is my 1 that I'm multiplying by here. Same thing in the numerator and the denominator. But I chose it so that I end up with this 1 minus cosine squared on the top, because I know that's a Pythagorean identity that would be helpful. 1 minus cosine squared is equal to sine squared. And my denominator is still sine theta times 1 plus cosine theta. Well, now I have sine squared in the numerator and sine in the denominator, So I can cancel one of those out. I'm going to cancel the sine out and just the squared, and I'm left with sine theta on top and 1 plus cosine theta on the bottom, which I do believe matches the other side. All right, let's look at the last section here. These are all equations, and we're going to be solving for x between 0 and 2 pi, including 0, not including 2 pi. Now remember, on these harder equations, one thing that we need to always try to do is get the equation in terms of one trig function. There's different ways to do this. Like on number 13, I've got the sine squared, and I also have cosine squared. I could change sine squared to be 1 minus cosine squared. I could change cosine squared to be 1 minus sine squared. We can do it on either side. I think I'm going to keep the left side as it is. Sine squared x plus 1 equals, and in cosine squared, I'm going to change that to 1 minus sine squared. So now, since I see quadratics, typically that means we're going to have to factor. So I'm going to move everything to one side. If I add sine squared, then I get 2 sine squared x. And if I subtract 1, well, my 1's cancel out. And so I'm just left with 2 sine squared x equals 0. I'm going to divide by 2, since there's really nothing here to factor. 0 divided by 2 is still 0. And I guess technically I can square root both sides. But the square root of 0 is still 0. So sine x has to equal 0. And that happens when x is 0 and pi. All right, let's move on to the next question, number 14. Now this question, a little bit tricky. We have everything in terms of sine, so that's good. But notice we've got this x over 2. Sine of x over 2. So I need to use one of my half angle identities because I really need everything in terms of just sine x. So over here on the left, sine squared x, that's going to stay the same, equal to 2 times, and actually let me rewrite this right side here. 2 sine squared of x over 2 is really the same as 2 times sine of x over 2 squared. Remember that we use that strange notation where we put the squared right next to the trig function. But it could be written with the whole thing, including the angle, in parentheses and squared on the outside. So that's how we're going to think about this, because that sine of x over 2, I'm going to change that to the identity 1 minus cosine x over 2. And that whole thing is squared, which is really convenient because the square root and the squared are going to cancel out. And I get 2 times 1 minus cosine x over 2. And notice my 2's can cancel out here as well because they are being multiplied. This 2 in the top is being multiplied, and so we can cancel it. So now on my right side, I have a cosine. And so that means I really need this whole equation to be in terms of cosine. And so on the left side, where I have that sine squared x, I'm going to change that to 1 minus cosine squared x. So now I have 1 minus cosine squared. Let me go ahead and write it again just to be more clear. 1 minus cosine squared is equal to 1 minus cosine x. And I've got a quadratic, so that means I'm probably going to have to factor. I need to get everything on one side, get it equal to 0. So, and I'm going to move everything to the right side because I like my quadratic term to be positive. So first of all, I'm going to subtract 1. If I subtract 1 from both sides, the ones cancel out. So I'm going to add cosine squared over, and we get cosine squared x minus cosine x equal to 0. So now I just have two terms, and so they both have a cosine. So I'm just going to factor out a cosine x. And if I do, on the inside I'm left with cosine x minus 1. And now that we're factored, I'm going to set each factor equal to 0. Let's go over here. Cosine x equals 0, or cosine x, whoops, it's minus 1, sorry, minus 1 equals 0. So if cosine x equals 0, that means x must be pi over 2 or 3 pi over 2. That's where cosine is 0. And then for my other factor, cosine x equals 1. And that happens whenever x is 0 radians. And so those three solutions would be the solutions to this equation. Let's move on to number 15, cosine 2x plus sine x. So I've got a double angle here. I'm going to look at my double angle identities, and if you look at your foldable, you'll see that for cosine 2x, you've got three choices of what you could substitute in. Since my other term has a sine in it, then for cosine 2x, I'm going to choose 1 minus 2 sine squared x plus sine x equals 0. If I choose that one, then my whole equation is in terms of sine, and that's something that I can solve. Again, I have a quadratic. Whenever you see a quadratic, we need to factor. I already have one side equal to 0, but I need to get my terms in order. I want the quadratic term to be first, and I also, as you know, I like that quadratic term to be positive. So I'm going to change all of my signs. And we're going to make this 2 sine squared x minus sine x, because I'm changing all the signs, minus 1. And this would be equal to 0. So now we're ready to factor. To get 2 sine squared, that's going to have to be 2 sine x times sine x. And to multiply to get 1, it has to be 1 and 1. I want to end up with a negative sign in the middle, so that means I want my negative over here so that it gets multiplied by the 2. I want my plus to be here. So now I'm factored. I'm going to set each factor equal to 0. 2 sine x plus, oh, my pen stopped working there, plus 1, there we go, equals 0. Or sine x minus 1 equals 0. I'm going to do the left one first. I'm going to subtract 1 from both sides and divide by 2. And so we need to figure out where sine is equal to negative 1/2. Well, first of all, let's think about where sine is negative. That's quadrants 3 and 4. And sine is 1/2 at the pi over 6 angle. In quadrant 3, that angle is 7 pi over 6. And in quadrant 4, it's 11 pi over 6. All right, on the other factor, I'm going to add 1 to both sides. Sine x is equal to 1. That happens at pi over 2. All right, last question. 2 cosine of 5x equals 1. Well, I've got this 5x here, and I don't have an identity for a 5x, and so we're going to have to work this a different way. I'm going to go ahead and solve for cosine 5x, and we get that cosine 5x is equal to 1/2. If I look at my unit circle, I can see that cosine is 1/2 at pi over 3, and also at 5 pi over 3, because cosine is positive in quadrant 1 and quadrant 4. And so what that means is that 5x is going to be equal to pi over 3. 5x is also going to be equal to 5 pi over 3. And then I can solve those. If I divide by 5, I'm going to get x equals pi over 15. And if I divide by 5 on my other one, x equals 5 pi over 15, which actually reduces to pi over 3. When I divide by 5, it actually cancels the 5 out in the numerator. So I've got two answers here. But remember, on these problems where I have a multiple angle, we're going to end up with more than just two answers. We're solving here for x between 0 and 2 pi. And if x is between 0 and 2 pi, that means 5x is going to be between 0 and 10 pi. If I multiply 2 pi times 5, we get 10 pi. And that means that I'm going around the unit circle 5 times to get to 10 pi, which means in each rotation around the unit circle I get two answers. We've already got two answers here for our first rotation, but I need to get 10 answers total. So let's think about this. In the next rotation, in my first rotation, we got pi over 3. I'm going to hit that same angle and get a coterminal angle 2 pi later, which means really what I want to do is add 2 pi to pi over 3, but I'm going to change 2 pi to be 6 pi over 3 so that I have a common denominator. So 1 pi over 3 plus 6 pi over 3. Here, let me write that here. I'm adding 6 pi over 3, which is really like adding 2 pi. And that's what we always do when we're trying to find coterminal angles. That's what we're trying to do here. I'm adding 6 pi over 3. So when I do that, I get 7 pi over 3. And if I add 6 pi over 3 to my other angle that I found previously, to the 5 pi over 3, if I add 6 pi over 3 there, then we get 11 pi over 3. So that's my second rotation around the circle, but remember we need to go around, unfortunately, 5 times. So I'm going to add 6 pi over 3 to both of these angles. If I add 6 pi over 3 to 7 pi over 3, I get 13 pi over 3. And if I add to 11 pi over 3, I get 17 pi over 3. So now we've gone around 3 times. Let's add again. If I add 6 pi over 3 to 13 pi over 3, I get 19 pi over 3. And if I add to 17, I get 23 pi over 3. And that's 4 times around. I just got to go one more time. 25 pi over 3. And then if I add 6 to 23, I get 29 pi over 3. So finally, we've got 10 angles, but these are all equal to 5x. I need to solve for x, and so I need to divide all these angles by 5, but notice what happened in the first one when we divided by 5. I ended up with, it just changed my denominator to be 15, and the same thing happened for 5 pi over 3, except the 15 did reduce back to 3, but originally when we divided by 5, we had a denominator of 15. And so that's what's going to happen for these. If I divide by 5, this becomes 7 pi over 15, 11 pi over 15, 13 pi over 15, 17 pi over 15, 19 pi over 15, 23 pi over 15, 25 pi over 15, and finally 29 pi over 15. And if you look at that last angle that we figured out, this angle, it is still less than 2 pi. That angle is less than 2 pi because if I'm in 15ths, 2 pi would be 30 pi over 15. 29 pi is still smaller than that, and so all of those angles are in the range that we're interested in. Those are all the answers to this particular equation.